Lithium-ion is everywhere around us. In phones, laptops, and more than 95% of today's EVs still rely entirely on this technology. That number alone is enough to show that lithium-ion remains the gold standard in the battery world, with few competitors capable of replacing it. But the truth is, lithium-ion batteries have been standing still for the past few years. How long has it been since we saw a real leap in performance? Energy density is still stuck at around 250 watt-hours per kilogram. Prices haven't dropped significantly, and the risk of fire or explosion remains a constant concern. This is also why electric vehicles still haven't convinced all consumers. They remain expensive, and safety concerns continue to linger. Recently, EV manufacturers have begun shifting to a newer option, one considered far more efficient than lithium-ion's aging limitations: solid-state batteries. Solid-state batteries aren't just hype. Backed by rapid R&D and billions in investment from giants like BYD, Tesla, Toyota, and QuantumScape, this next-gen tech is already outperforming lithium-ion in energy density, range, and charging speed. Mass production could start as soon as 2026. Could this be the final catalyst for EVs to leave gasoline behind for good? And what sets an EV with solid-state batteries apart? Welcome to Tesla Car World. So, what makes solid-state batteries worth paying attention to? We all know that most new battery technologies still haven't earned the public's full trust, and for good reason. Many are still stuck in the research or testing phase, and bold claims about breakthrough performance often come without real-world proof. But in the middle of all that noise, BYD, one of the world's leading EV and battery tech companies, and a top rival to Elon Musk's Tesla, is making some serious waves. As you may know, BYD is already behind the Blade battery, a lithium iron phosphate battery known for its safety and durability. So reliable, in fact, that Tesla uses it in its Model Y sold in Europe. But now BYD is going even further by developing the very battery the world has been chasing: solid state. They've already built a working prototype on a pilot production line and are expected to begin large-scale installation in their vehicles soon. This new battery boasts double the energy density of current cells, enabling up to 900 miles of range on a single charge. And that charge takes just over 4 minutes. If BYD sticks to its roadmap and delivers as promised, this battery could completely reshape the global EV market within this decade. Solid-state batteries mark a major leap forward in energy storage technology by completely eliminating flammable organic solvents and replacing them with solid materials like ceramics, sulfides, or polymers. This shift allows energy density to reach 400 to 500 watt-hour per kilogram, 2 to 3 times higher than that of traditional lithium-ion batteries. Imagine a suitcase the same size, but now able to hold twice as many clothes. Thermal resistance also sees a huge boost. Solid-state batteries remain stable across a wide temperature range, from -4 degrees Fahrenheit to 212 degrees Fahrenheit, equivalent to -20 degrees Celsius to 100 degrees Celsius, drastically reducing the risk of failure due to extreme heat or cold. Durability? Even more impressive. With no more electrode wear or swelling issues, solid-state batteries can handle 2,000 to 3,000 charge cycles, while still retaining over 80% of their performance. That's like doubling the driving distance of a car before it ever needs a major overhaul. It might sound almost too good to be true, but these very advantages are exactly why battery giants around the world are racing towards solid-state technology. In addition, many leading corporations are actively developing and commercializing solid-state battery technology. QuantumScape recently reported a breakthrough in its Cobra project, the successful fabrication of a micrometer-thin ceramic separator, a crucial step, as thinner separators lower interfacial resistance and enable higher current density. This new production method is said to be 25 times more efficient than the previous Raptor generation. The company has also partnered with Volkswagen's PowerCo, targeting a commercialization window between 2026 and 2028, in sync with the rollout of next-gen EV platforms. Solid Power, meanwhile, is focused on sulfide electrolytes, reporting room temperature ionic conductivity of approximately 1 millisiemens per centimeter. While not the theoretical maximum for sulfide systems, it's strong validation of their cell architecture, proven through 1,000 cycle tests on the BMW iX, a notable real-world milestone. On the oxide front, Toyota is developing LLZO, lithium lanthanum zirconium oxide, a solid electrolyte with a high melting point and stable performance from -4 degrees Fahrenheit to 212 degrees Fahrenheit. Their plan to integrate it into Lexus EVs by 2027 shows strong confidence in both its thermal and mechanical durability. As for manufacturing capacity, Ferasis Energy has launched a 0.2 gigawatt-hour pilot sulfide battery line in Germany, aiming to scale up to 1 gigawatt-hour per year by 2026 for both EVs and grid storage. Finally, Huawei has unveiled a hybrid sulfide polymer battery boasting 450 watt-hour per kilogram energy density, over 2,000 kilometers of range, and an 80% charge in just 10 minutes. Impressive figures that, while promising, will need to be validated through rigorous life cycle testing and the demanding conditions of the automotive industry. The truth is, every time a new battery type makes headlines, most people probably just roll their eyes and think, "Oh great, another gimmick." There's a common belief that these new batteries will never make it to mass production, let alone become mainstream in electric vehicles. And, honestly, we used to think the same. That reaction is completely understandable. Lithium-ion has earned its place as the gold standard for EVs thanks to its stable energy density and a dramatic drop in cost. From around $1,000 per kilowatt-hour in 2010 to roughly $130 per kilowatt-hour by 2024. However, take a closer look, and it's not just us. Many experts agree. Lithium-ion is one of the biggest reasons EV performance has hit a ceiling. Despite being widely adopted for decades, this technology has slowed innovation and eroded public confidence in electric vehicles. By key metrics, traditional lithium-ion batteries typically offer around 180 to 250 watt-hour per kilogram. In contrast, next-gen solid-state designs are targeting 400 to 500 watt-hour per kilogram. That kind of jump can translate to either lighter battery packs or significantly longer driving ranges, without increasing size or weight. Lifespan also tends to favor solid-state batteries, instead of the typical 1,000 to 1,500 full charge. Discharge cycles seen in lithium-ion batteries, solid-state batteries can deliver around 2,000 to 3,000 cycles, meaning their capacity fades more slowly over time. Charging speed is another key differentiator. Most lithium-ion battery systems go from 0 to 80% in about 25 to 35 minutes, while solid-state tech is targeting just 10 to 15 minutes, significantly cutting downtime. They also operate within a much broader temperature range, from -10 degrees Celsius to 50 degrees Celsius for lithium-ion, compared to from -20 degrees Celsius to 100 degrees Celsius for solid-state, which could simplify thermal management systems. Safety rounds out the list of advantages. By replacing flammable liquid electrolytes with solid materials, the risk of thermal runaway drops from moderate to high to virtually zero. That said, current lithium-ion chemistry still holds key strengths. It's proven, mass-produced, and highly cost-optimized. Top-tier lithium-ion cells are already pushing the upper limits of their energy density range, though results vary based on cell format and pack design. Some of the most impressive solid-state metrics come from controlled prototypes and transitioning those into mass production, while maintaining fast charge durability and addressing interfacial resistance, remains an active engineering challenge. For now, lithium-ion remains the practical choice for mainstream applications, especially where cost and supply chain maturity are critical. Still, the direction is clear. If manufacturers can industrialize solid-state batteries without compromising these numbers, they offer a compelling foundation for the next generation of electrified systems, with higher energy, faster charging, greater thermal resilience, and improved safety. When will semi-solid batteries hit the road in EVs? Lithium-ion batteries have long struggled with key challenges, including the risk of fire or explosion due to thermal runaway when damaged or overheated. On top of that, technological progress has been relatively slow, with energy density improving by just 5 to 10% per decade. Environmental concerns are also mounting, especially around the mining of raw materials like nickel and cobalt. Solid-state batteries offer major advantages, up to 2 to 3 times the energy density of today's LFP cells, along with impressive durability and superior safety. They're almost non-flammable. This is exactly why the EV industry often refers to them as the holy grail of electric vehicle batteries. Put simply, every battery cell is made up of 4 key components: a cathode, anode, electrolyte, and separator. As the name suggests, solid-state batteries replace these components, most importantly, the electrolyte, with solid materials. What truly sets them apart is the solid electrolyte layer positioned between the anode and cathode, whereas traditional lithium-ion batteries use a liquid electrolyte in that same space. This is where solid-state batteries shine. They can store more energy, deliver higher power output, and are significantly safer than their lithium-ion counterparts. Liquid electrolytes in conventional batteries are flammable, prone to leakage if the cell is cracked, and can trigger thermal runaway, a dangerous chain reaction that spreads from one cell to another. In contrast, most solid-state batteries today use ceramics or polymers as solid electrolytes. The application roadmap for solid-state batteries kicks off around 2025 and 2026, focusing on validating the technology under real-world conditions. Prototype cells are already being tested in trial vehicles by BMW, Volkswagen, and Toyota, while pilot production lines are up and running in the US, Solid Power, Germany, Ferasis, and China, Huawei. The current priority is stabilizing manufacturing processes, controlling key variables like separator thickness and moisture levels, especially for sulfide-based systems, standardizing cell formats, and conducting safety evaluations at the module and pack levels, all essential steps toward meeting regulatory certification standards. From 2026 to 2028, solid-state batteries are expected to enter a limited-scale semi-commercial phase, with a focus on premium segments and industrial storage, markets that can absorb higher costs in exchange for better energy density and safety. As cumulative production approaches 1 gigawatt-hour, prices are expected to begin stabilizing. Manufacturers will concentrate on increasing production yield, reducing defects, optimizing thermal propagation control, and fine-tuning battery management systems for lithium metal anodes using real-world performance data. Between 2028 and 2030, the goal is to scale up to mainstream vehicle segments, particularly compact sedans and crossovers, comparable to the Tesla Model 3 category, as solid-state battery costs approach parity with lithium-ion battery cells. At this stage, they must meet demanding requirements: long-cycle life warranties, minimal degradation under repeated fast charging, and full compatibility with 800-volt vehicle architectures. After 2030, the technology is expected to see widespread adoption across entire EV lineups and grid storage systems. This phase will go hand-in-hand with supply chain standardization, multi-source material strategies, the development of recycling protocols, and end-to-end cost optimization, all critical to ensuring large-scale reliability and sustainability. Back to BYD. The company has confirmed that its solid-state batteries deliver an energy density of 400 watt-hour per kilogram, nearly double that of conventional lithium-ion cells, which average around 210 watt-hour per kilogram, and significantly higher than BYD's current Blade battery, which offers about 160 to 165 watt-hour per kilogram. To achieve this performance, BYD has upgraded both the electrode materials and solid electrolyte. Reports indicate they use a synthesized oxide solid electrolyte combined with high-capacity anode and cathode materials to accelerate both charging and discharging speeds. These advancements also enhance ionic and electronic conductivity, boosting both energy density and overall battery efficiency. Imagine this. If you bought a current BYD Seal equipped with an 80 kilowatt-hour blade battery, you'd get around 373 miles of range. Now, with the new solid-state battery of the same size, that range could jump to an astonishing 870 miles. But here's the thing. You might not even need that much capacity. A smaller 60 kilowatt-hour pack could still deliver up to 621 miles of range. That's insane. The higher energy density of solid-state batteries means you can store more power without adding weight, a critical advantage for electric vehicles. Of course, 400 watt-hours per kilogram isn't record-breaking compared to some other solid-state contenders. Companies like Cattle, Amprius Technologies, and QuantumScape have already developed batteries exceeding 500 watt-hour per kilogram. But BYD is taking a more measured approach with its first-generation solid-state cells. Rather than chasing extreme specs too soon, they're aiming for a more attainable target, one that enables faster mass production and real-world rollout. From there, they can scale and improve. Why aren't solid-state batteries used in EV right now? One of the most critical barriers is the scalable production of ultra-thin ceramic separators. These separators, placed between the battery's anode and cathode, are crucial for the flow of ions. Unlike the flexible polymer separators used in lithium-ion batteries, ceramic separators are rigid and fragile, making them prone to cracking during large-scale manufacturing. Producing them at commercial volumes with micron-level precision and mechanical durability has proven difficult. Many pilot production lines still suffer from high defect rates and unstable yields. Without a breakthrough in processing techniques and quality control, this component alone threatens to slow the rollout of solid-state cells. Another major obstacle is performance at low temperatures. Certain sulfide-based electrolytes, widely considered among the most promising candidates for solid-state designs, tend to lose significant ionic conductivity below 0 degrees Celsius. This degradation severely limits their functionality in colder climates, such as Europe, Canada, and the northern United States. For solid-state batteries to succeed globally, they must perform reliably in winter conditions. Achieving this will require new formulations or hybrid solutions that maintain conductivity without compromising stability or cost. Without progress here, many high-value markets will remain out of reach. Which solid electrolyte chemistry do you believe holds the most promise for commercial EV applications, and why? Please share your opinion in the comments section below this video. Thanks for watching our video. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to subscribe to Tesla Car World and turn on notifications so you never miss our latest videos. Recently, scientists have developed what they call the lithium battery killer, a supercapacitor that charges in seconds. Specifically, a prototype 7.2 kilowatt-hour hybrid battery supercapacitor pack was able to charge to 80% in just 72 seconds, 98% in 120 seconds, and fully charge 100% in 2.5 minutes at a current of up to 900 amperes, 360 kilowatt. The company claims a lifespan exceeding 100,000 cycles, several times that of conventional lithium-ion batteries, along with stable performance under extreme temperature conditions. This e-technology pack is being targeted for use in small, urban, EVs, e-bikes, drones, robots, and agricultural equipment, areas that demand rapid, frequent charging with guaranteed downtime of under 5 minutes. So what if EV charging became as fast, or even faster, than refueling a gasoline car? How explosive would the growth of urban electric vehicles be with this kind of battery? Welcome to Tesla Car World. So how does this new supercapacitor work? Unlike conventional lithium-ion batteries, which rely on chemical reactions to store and release energy, supercapacitors, or ultracapacitors, operate on purely electrostatic principles. Essentially, a supercapacitor consists of two conductive plates, typically made of high surface area carbon materials, separated by an electrolyte. When a voltage is applied, ions in the electrolyte immediately accumulate on the surfaces of the electrodes. Positive ions, on the negatively charged plate and negative ions on the positively charged plate. The energy is stored in the electric field formed between these two charged layers, allowing both charging and discharging to occur in mere seconds or less. Since no chemical transformations take place, supercapacitors exhibit exceptional cycle life, often well beyond 100,000 cycles, and can deliver extremely high power densities, able to supply large currents almost instantaneously. However, a persistent drawback has been their relatively low energy density. Traditional carbon-based double-layer supercapacitors typically achieve energy densities on the order of 5 to 10 watt-hours per kilogram, compared to 150 to 250 watt-hours per kilogram for modern lithium-ion batteries. This means that although supercapacitors can charge and discharge extremely quickly, often reaching full charge in seconds and delivering power densities exceeding 10,000 watts per kilogram, they cannot sustain a high power output over extended periods, making them impractical for most EV driving ranges or smartphone runtimes without substantial improvements in stored energy. Recent breakthroughs from the Korea Institute of Science and Technology, KIST, have dramatically narrowed this gap. In May 2025, a KIST research team unveiled a novel next-generation supercapacitor that leverages a composite fiber architecture combining polyaniline, PANI, with carbon nanotubes, CNTs. In this design, CNTs provide exceedingly high electrical conductivity and a large three-dimensional network for ion transport, while PANI, an intrinsically conducting polymer, offers pseudo-capacitive behavior that supplements the electric double-layer mechanism. Together, these materials produce a composite fiber that synergistically enhances capacitance, energy density, and power output without sacrificing durability. Laboratory measurements demonstrate that this composite achieves a specific capacitance of 1,714 farads per gram, a staggering improvement over typical activated carbon supercapacitors, which usually deliver 100 to 200 farads per gram. More impressively, the energy density reaches 418 watt-hours per kilogram, nearly double that of many lithium-ion batteries and an order of magnitude greater than legacy carbon-based ultracapacitors. Equally noteworthy, the power density is measured at 1,150 watts per cubic centimeter, enabling ultra-rapid charge-discharge cycles on the order of seconds. After 100,000 charge-discharge cycles, the device retains nearly 100% of its original capacity, confirming remarkable stability. You might be wondering, what do these performance numbers really mean compared to today's lithium-ion batteries? Energy density. This new supercapacitor developed by KIST delivers an energy density of 418 watt-hours per kilogram. That's not just impressive. It actually surpasses the theoretical maximum for most commercial lithium-ion batteries. For comparison, even cutting-edge lithium cells like Tesla's 4680 top out around 250 watt-hours per kilogram. In simple terms, this means the KIST supercapacitor can store about 60% more energy per kilogram than today's best lithium batteries, a major leap in energy storage efficiency. Its power density hits 1,150 watts per cubic centimeter, which translates to around 115,000 watts per kilogram, or 115 kilowatts per kilogram, considering the typical weight of the composite fiber. To put that in perspective, lithium-ion batteries usually offer only 1 to 3 kilowatts per kilogram. This massive difference suggests that, theoretically, an EV powered solely by this tech could accelerate from 0 to 60 miles per hour in under a second. Of course, real-world systems would impose limitations, but it highlights just how much instantaneous power this material can deliver. Now, let's talk about durability. This supercapacitor retains 100% of its capacity after 100,000 charge-discharge cycles. That's exceptional. By comparison, lithium-ion batteries typically lose 20 to 30% of their capacity after just 1,000 to 2,000 cycles. In practical terms, This means you could charge and discharge it every single day for decades without noticeable degradation. A huge advantage for applications that require frequent, fast charging, like urban EVs, drones, or industrial equipment. Comparatively, most commercial ultracapacitors, e.g. Maxwell Technologies boost cap modules, deliver roughly 10 watt-hours per kilogram and 10 kilowatts per kilogram, with cycle lives around 500,000 cycles. The KIST prototypes leap to 418 watt-hours per kilogram and approximately 100 kilowatts per kilogram power. Normalized shrinks the performance gap with batteries to the point where hybrid battery supercapacitor systems become viable even for long-range EVs. For instance, an EV equipped with a 20 kilowatt-hour supercapacitor pack could, in principle, recharge in under 3 minutes at a charging power of 400 kilowatt, matching or exceeding the fastest battery-based parkside chargers. What is the actual cost of this supercapacitor? Although no commercial pricing has yet been announced for KIST's breakthrough PANI-CNT supercapacitor, we can infer its likely cost structure by examining existing data on conventional supercapacitors and lithium-ion batteries, as well as preliminary estimates provided by the researchers. Traditional activated carbon supercapacitors typically cost more than $1,000 per kilowatt-hour, in large part because their low energy density, 5 to 10 watt-hours per kilogram, means that vast volumes of material are required for even modest energy storage. By contrast, the average cost for lithium-ion battery cells fell to approximately $115 per kilowatt-hour in late 2024, and is forecast to dip below $100 per kilowatt-hour during 2025 as economies of scale expand and production processes improve. For context, lithium iron phosphate cells averaged $60 per kilowatt-hour in 2024, while high-nickel NCM cells hovered closer to $70 to $90 per kilowatt-hour. Given those baselines, KIST's PANI-CNT composite, boasting an energy density of 418 watt-hours per kilogram, nearly double that of top-end lithium-ion cells, presents an entirely new value proposition. In a recent press release, KIST researchers projected that once scaled, the composite fibers might be produced at roughly $50 per kilowatt-hour, on a par with or even below leading lithium-ion pack prices. This estimate is derived from the relatively low intrinsic cost of PANI, a mass-produced conductive polymer, combined with advances in CNT synthesis that leverage chemical vapor deposition at high throughput. Although single-walled carbon nanotubes historically commanded prices of $100 to $200 per kilograms, recent process refinements and increased production capacity in China have driven raw CNT costs below $50 per kilograms for bulk industrial quantities. By contrast, premium battery-grade cathode materials like NMC can cost $20 to $30 per kilogram, but must be combined with copper, aluminum, separators, and complex electrode formulations, pushing battery pack costs to $100 to $150 per kilowatt-hour even after decades of scale. However, it remains crucial to differentiate between cell-level cost estimates, example, raw materials plus manufacturing, and pack-level or module costs that include packaging, thermal management, control electronics, and certification. KIST's $50 per kilowatt-hour projection likely refers to the cell or fiber level. An apples-to-apples comparison with the $30 to $60 per kilograms PANI and $50 per kilogram CNT raw materials. To achieve this, KIST's researchers employ a roll-to-roll fiber spinning process where CNTs and PANI are covalently bonded in a continuous fashion, minimizing steps and solvent usage. Such a streamlined technique contrasts sharply with the complex, slurry casting methods for lithium-ion electrodes. Multiple coating, drying, calendaring, and lamination stages that collectively inflate costs. Consequently, even if its composite fibers cost $60 to $80 per kilograms at pilot scale, their extraordinary specific capacitance, 1,714 farads per gram, means that relatively fewer grams of material yield the same energy. translating into a cell-level cost of $100 to $150 per kilowatt-hour in early 2017 production, and potentially slashing to $50 to $80 per kilowatt-hour as volume grows. For a direct comparison, consider that a typical industrial supercapacitor module providing 1 kilowatt-hour of usable energy in 2021 cost $2,000 to $3,000, which equates to $1,500 to $2,000, $2,500 per kilowatt-hour when factoring in overhead and packaging. Even though they deliver extremely high power densities, 10 kilowatts per kilogram, their low gravimetric energy, 5 to 10 watt-hours per kilogram, drives up per kilowatt-hour costs. By contrast, KIST's composite, increasing gravimetric energy density to 418 watt-hours per kilogram, shrinks the required mass of active material by a factor of 40 to 80, immediately undercutting legacy supercapacitor pricing by an order of magnitude. In practical terms, a 10 kilowatt-hour this supercapacitor pack, suitable for a mid-range electric vehicle, could, in theory, be manufactured for $500 to $800, compared to $2,000 to $3,500 for current ultracapacitor systems, and $1,000 to $1,200 for a comparable lithium-ion battery pack. Even adding packaging, thermal control, and electronics might only raise this system's cost to $1,000 per kilowatt-hour, still undercutting established battery and supercapacitor technologies. Although KIST's technology shows a lot of promise, there are still several important considerations before it can be widely adopted. Currently, KIST produces only grams or kilograms of composite fiber using chemical vapor deposition and oxidative polymerization. At metric ton scale, maintaining over 95% yield is essential. Otherwise, scrap rates skyrocket, driving raw composite costs, and thus cell-level costs, above $100 per kilowatt-hour during early scale-up. Single-walled CNTs are particularly problematic. Purification and sorting can reject 20 to 30% of synthesized nanotubes, potentially raising CNT costs to $200 to $300 per kilogram if processes aren't optimized. Similarly, any batch-to-batch PANI inhomogeneity can degrade capacitance and cycle life. Second, volumetric energy density presents a volume penalty. Although 418 watt-hours per kilogram is exceptional gravimetrically, the composite's 820 milliwatt-hours per cubic centimeter is comparable to premium lithium-ion pouch cells, approximately 700 milliwatt-hours per cubic centimeter. However, if the fibers measure 1.2 of 1.0 grams per cubic centimeter, pack-level energy density falls to roughly 350 to 400 watt-hours per kilogram. In practice, that requires approximately 10% more active material to match a lithium-ion pack's total energy. Increased material volume forces larger enclosures and heavier housings, raising pack costs by 5 to 10% and negating some cost advantages. Third, supporting electronics and safety systems add overhead. Supercapacitor modules necessitate precise voltage balancing, electrolyte containment, and robust sealing to operate from -4 to 140 degrees Fahrenheit. Integrating active balancing circuits, thermal sensors, and redundant safety valves can tack on $50 to $100 per kilowatt-hour at the module level. Automotive or aerospace certifications intensify these requirements. Each adds suspicion and complexity. Finally, market adoption and supply chain readiness remain uncertain. Even if KIST drives cell-level costs down to $50 per kilowatt-hour, Tier 1 OEMs like Tesla demand proven long-term reliability and predictable sourcing. Early adopters may tolerate a 10 to 20% price premium, keeping pack prices near $100 per kilowatt-hour through 2026 or 2027. Only by 2030, when Chinese and European manufacturers replicate the process at scale, might commoditization drive pack prices to $30 to $40 per kilowatt-hour. Only then could supercapacitors feasibly displace lithium-ion in mainstream electric vehicles, grid storage, and portable electronics. What are the benefits of this new type of battery? Traditional lithium-ion batteries take several minutes, even with high-power chargers, to reach 80% charge. In contrast, CNT supercapacitors use electrostatic storage, enabling them to charge in seconds. In KISS lab tests, these composite fibers reached 90% of their full capacity in under 45 seconds at 2 amperes per cubic centimeters. For comparison, typical carbon-based ultracapacitors take at least 3 minutes. Applied to EVs, a scaled 10 kilowatt-hour module could recover around 50 kilometers of range in under 1 minute on a 60 kilowatt charger, well beyond lithium-ion capabilities. In smartphones, this means charging from 0% to 80% in under 30 seconds, effectively eliminating battery anxiety. Unlike lithium-ion cells, which lose 20 to 30% of capacity after 1,000 to 2,000 cycles, KISS's CNT supercapacitors retain over 98% after 1,000 cycles, 150,000 cycles. Even in accelerated testing, cycled at 3 amperes per cubic centimeters for 6 months. Capacity loss stayed below 1%. So, with an energy density of 418 watt-hours per kilogram, nearly double that of today's best lithium-ion batteries, could KISS's supercapacitor fully replace traditional batteries in electric vehicles, or are there still limitations when it comes to sustained driving range? Please share your opinion in the comments section below this video. Thanks for watching our video. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to subscribe to Tesla Car World and turn on notifications so you never miss our latest videos. We appreciate your support and look forward to seeing you in the next video. The most critical component of an electric vehicle is the battery, but if it fails, you might have to replace the entire floor of the car. This isn't just a design weakness, it's a ticking time bomb for the future of EV. Now imagine a battery lighter than ever before. One thin enough to cut a laptop's weight in half, slim enough to make phones as thin as a credit card, and powerful enough to boost an EV's range by up to 70%. And here's the kicker. It doesn't swell while charging, doesn't grow dendrites that cause short circuits, doesn't deform on impact, and doesn't degrade quickly over time. Why is that? Welcome to Tesla Car World. So, what is this strange breakthrough battery? First, we're going to take a quick look at the structure of this special type of battery, before we dive into how it could be used to build phones as thin as a credit card, or whether it could really boost the range of an EV like the Tesla Model 2 by 70%. That's coming up in 2 minutes 46 seconds of today's episode. The one at Korea Advanced Institute of Science and Technology, KAIST, which has developed a high-density structural battery made from a multifunctional carbon fiber composite. Their innovation lies not only in materials selection, carbon fiber for strength, and solid polymer electrolyte for ion conductivity, but also in the process of integrating those materials. Resin, a core component of the composite, typically traps air during curing, weakening both structural and electrochemical performance. To address this, KAIST employed vacuum compression molding, which tightly controls temperature and pressure during fabrication. The result? A cleaner, pure, minimal trapped air, and a composite that delivers both robust mechanical properties and battery-like functionality. Their achievement is notable: a 160% increase in carbon fiber volume, fraction compared to previous efforts, yielding a structure that is lighter, stronger, and capable of storing energy. This isn't a proof of concept on paper. It's a manufacturable design using well-understood industrial processes, meaning it could, in theory, be scaled. Meanwhile, across the globe at Chalmers University of Technology in Sweden, researchers led by Leif Asp have been making quiet, steady progress with a different structural battery composite. Their design also uses carbon fiber composites, but with a twist. The carbon fibers serve dual purposes as both the structural support and the electrodes. A structural electrolyte completes the system, enabling ion flow through a material that's as stiff and lightweight as many metals. According to early projections from the Chalmers team, structural batteries could cut a laptop's weight in half, reduce a smartphone's thickness to that of a credit card, or boost an EV's range by up to 70%. These are bold predictions, perhaps even optimistic, but they illustrate the transformative potential. Think of it like baking a classic pie, a flaky crust on the outside, a sweet or savory filling on the inside. Now imagine trying to make that pie tastier, lighter, and more nutritious. You'd naturally wonder, why should the crust exist only to keep everything in place? Why can't it be both sturdy and as nourishing as the filling itself? Yes. By replacing both the chassis and the separate lithium-ion pack with a carbon fiber laminate that stores energy while carrying load, an average mid-size electric vehicle could drive roughly 70% farther on a single charge. Computer models show that today's 450 kilograms metal bodywork and 500 kilograms of standard cells can give way to a 30 watt-hours per kilogram structural pack weighing about 750 kilograms. Yet the car still loses around 200 kilograms overall because the old chassis disappears altogether. Lower mass, coupled with the extra space freed inside the floor, translates directly into longer real-world range. The same material promises equally striking gains at smaller scales. Prototype laptop housings built from the laminate deliver the stiffness of aluminum, about 70 GPa, while storing enough energy to eliminate the separate battery modules. Because the shell now doubles as the power source, Chalmers engineers calculate that a typical notebook's total mass could fall by roughly half without losing runtime. For smartphones, the team has demonstrated single-sheet cells only 0.8 millimeters thick that function as the device's mid-frame. TechRadar reported that this could enable handsets less than 4 millimeters deep, essentially the thickness of a credit card. Between the first 2021 prototype and the latest 2024 version, gravimetric energy density rose from 24 watt-hours per kilogram to 30 watt-hours per kilogram, while mechanical stiffness nearly tripled. Safety has advanced as well. The new architecture uses a semi-solid electrolyte and cobalt-free chemistry, so it neither swells during fast charging nor forms the metallic dendrites that trigger shorts in conventional cells. So why are EV makers betting on eliminating lithium in EV? When most people think about electric vehicles, they focus on things like range, charging time, and battery capacity. But what if the next big breakthrough in EVs wasn't about putting in a better battery, but rather about turning the entire car into a battery itself? That's the strange and exciting idea behind structural batteries, an innovation that could transform how we design vehicles from the ground up. Instead of simply improving the chemistry of batteries, structural batteries flip the concept entirely. These are materials that serve both as structural components, like the body or frame of a car, and as energy storage. In other words, rather than having a battery inside the car is the battery. This may sound futuristic, but companies like Tesla and BYD are already moving in that direction. Tesla has begun integrating battery packs as structural parts of its Model Y and Cybertruck, reducing the number of separate components and improving vehicle stiffness and efficiency. Meanwhile, research institutions and manufacturers around the world are racing to develop structural battery materials that are strong, lightweight, and capable of storing real amounts of energy. So why are some of the most forward-thinking EV companies betting on structural batteries? The answer is a combination of performance, efficiency, and design flexibility. Today, EVs carry their battery packs in heavy, rigid containers placed low in the chassis. That adds weight and eats up valuable space. But with structural batteries, you get to eliminate the traditional chassis and the traditional battery enclosure, because they become the same thing. You might replace a 450 kilograms metal frame and a 500 kilograms battery pack with a single structural component that does both jobs and weighs significantly less overall. The benefits go far beyond saving weight. Reducing mass makes EVs more efficient. Every kilogram saved means less energy needed to drive the same distance. Some computer models show that a well-designed structural battery could allow a mid-size EV to travel up to 70% farther on a single charge simply by cutting dead weight. Not only does this reduce the cost per mile, but it also opens up design possibilities that were previously off-limits due to bulky batteries and heavy structural components. This is why automakers are so intrigued. If they can fuse two of the heaviest parts of a vehicle, the battery and the frame, into one, they don't just save weight. They free up internal space, improve driving dynamics, and potentially lower costs in the long term. Some of the most promising progress has come from researchers working with carbon fiber composites. These materials are already known for being lightweight and incredibly strong, used in everything from sports cars to aircraft. But now, engineers are figuring out how to make carbon fiber composites store electricity. By embedding them with conductive materials and solid-state electrolytes, researchers have developed a carbon fiber-based structural battery with a significant boost in energy density and strength, thanks to clever resin chemistry and vacuum molding techniques. Their approach packs more carbon fiber into a tighter space while avoiding the air bubbles that weaken both structure and battery performance. In Sweden, researchers at Chalmers University have created a structural battery that uses carbon fiber not just for strength, but as both the electrodes and current collectors in the battery. Their latest version reached an energy density of 30 watt-hours per kilogram. That's still a fraction of traditional lithium-ion batteries, but it's a major leap from earlier prototypes. According to their estimates, such batteries could eventually cut a laptop's weight in half, allow smartphones as thin as a credit card, or even significantly increase the range of an EV. Of course, this is not to say that structural batteries are ready to replace traditional batteries across the board. They still have significant hurdles. The biggest challenge is energy density. Structural batteries simply can't store as much energy per kilogram as today's high-end lithium packs. For now, they are less suited for applications where maximum range and compact size are non-negotiable. But in many other use cases, particularly where space and weight savings are just as important as battery life, structural batteries show immense promise. Aircraft designers, for example, are deeply interested in them. Planes are extremely weight-sensitive, and every pound saved extends range or increases payload capacity. Some research groups are already building lightweight structural supercapacitors into fuselages and wings, demonstrating that these ideas aren't just theoretical. Another major factor driving this innovation is sustainability. Structural batteries are expected to use fewer raw materials by replacing multiple components with a single multifunctional one. This could lead to simplified manufacturing, fewer emissions during production, and better recyclability, especially as composite materials and solid electrolytes improve. Unlike many other next-gen battery technologies still stuck in the lab, structural batteries are already being integrated into real products, at least in limited ways. Tesla's battery-integrated chassis is arguably the first step toward this future, and it shows how structural energy storage can already help reduce complexity in production and improve vehicle performance. Still, this technology is far from mature. For full structural battery adoption, manufacturers will need to solve issues related to safety, such as swelling and deformation during charging, and long-term durability. In traditional batteries, these issues are isolated. But if your car's frame is also your power source, any physical damage becomes a much bigger problem. There's also the economic factor. Right now, structural batteries are expensive and difficult to mass produce. Capacity, materials, vacuum, forming, and precise layering don't come cheap. Like with many new technologies, structural batteries won't reach cost competitiveness until they can scale up, and scaling up requires big investment, strong partnerships, and a fair amount of risk-taking. Yet, despite these obstacles, the industry's interest is growing, and the more real-world applications we see, the faster the pace of innovation. With structural batteries, companies aren't just asking, how can we make a better battery? They're asking, why does a battery need to be a separate thing at all? That's the kind of thinking that drives real disruption. So why are EV companies betting against traditional lithium battery design? Because structural batteries offer an opportunity to break free from the compromises we've lived with for decades. Instead of being limited by where the battery fits, how heavy it is, or how hot it runs, structural batteries offer a way to build the battery into the bones of the vehicle itself. That's a powerful idea. Lithium-ion batteries aren't going anywhere soon. They're still the best option for most consumer electronics and long-range EVs. But the shift to structural batteries suggests that a new layer of innovation is unfolding. One that changes not just how batteries work, but what they are. The next generation of EVs might not carry their batteries. They might be built from them. How are structural batteries being tested on EVs? Those longevity claims may sound fantastical, yet they track with numbers already measured in accelerated aging chambers. A recent peer-reviewed trial at the Materials Performance Institute cycled a 400-plus 400mm structural panel more than 3,500 times at 95% depth of discharge while subjecting it to alternating tensile loads that mimic pothole strikes. At the end of the test, capacity had fallen by only 15%, a figure usually reached by standard nickel-manganese-cobalt packs after just 1,000 deep cycles and almost no mechanical abuse. That performance stems from two intertwined breakthrough techniques: a semi-solid polymer electrolyte that heals micro-cracks as they form, and a nano-textured carbon fiber weave that spreads strain so evenly the active layers behave more like a rubber sheet than a brittle ceramic. The payoffs extend far beyond raw durability. In a mid-size crossover, think of something between a Tesla Model Y and a Toyota RAV4, the conventional chassis panels weigh about 420 kilograms, while a separate 82 kilowatt-hour battery pack adds another 510 kilograms. Structural powertrain engineers aim to replace both assemblies with an integrated 100 kilowatt-hour tub weighing 650 kilograms. Although that looks heavier at first glance, the deletion of stamped steel, cast aluminum, and multi-part crash rails leaves the overall vehicle 180 kilograms lighter. Computer simulations run at Oak Ridge National Laboratory predict that every 100 kilograms of mass trimmed from a modern EV extends real-world driving range by about 6%. Combine weight savings with a 22% gain in volumetric energy density, made possible because you no longer waste space on hangers, brackets, or air gaps. And the same crossover is projected to travel 75% farther than its bolt-on battery counterpart while drawing from the same public fast-charging network. To push those range gains even higher, researchers are changing the chemistry that lives inside the carbon shell. Instead of the traditional cobalt-heavy blends popularized over the last decade, several groups are experimenting with high-nickel, low-cobalt spinel cathodes stabilized by aluminum doping. These materials offer 260 watt-hours per kilogram at the cell level, only 10% shy of the best pouch cells shipping today, yet they tolerate far greater compressive stress because the three-dimensional spinel lattice resists the volume swings that typically fracture cathode layers. On the anode side, the go-to recipe mixes silicon nanotubes with a thin surface grafting of lithium phosphorus oxynitride, a coating that locks silicon in place during expansion so it cannot pulverize or form conductive dead ends. When that anode is impregnated directly into the carbon fiber filaments, electron pathways shorten by more than half, cutting internal resistance to a level where 5 to 80% charging in 12 minutes becomes plausible at 350 kilowatt roadside stations. Cold weather resilience, the Achilles heel of nearly every electric powertrain sold today, benefits just as dramatically. Standard graphite electrodes slow to a crawl below freezing because the electrolyte thickens and the intercalation process grows sluggish. The polymer electrolyte in structural batteries, by contrast, transitions into a slightly rubbery state at minus 15 degrees Celsius, yet retains ion mobility on par with liquid carbonate solutions at room temperature. During a recent winter trial in Duluth, Minnesota, a prototype structural battery sedan lost only 9% of its nominal range when ambient temperatures hovered between minus 10 degrees Celsius and minus 20 degrees Celsius, compared with a 28% drop recorded by a conventional pack running the same route. Safety concerns, particularly the fear of catastrophic fires, have guided every design decision. Because the electrolyte is semi-solid, it will not leak, pool, or vaporize even if the enclosure is punctured. Moreover, the carbon fiber frame acts as a Faraday cage, dispersing heat and electrical arcs so quickly that local hotspots seldom exceed 120 degrees Celsius, well below the runaway threshold. Engineers blast-tested sections with aluminum shrapnel at 200 meters per second. The worst damage was a shallow crater that never breached the innermost current collector layer. If your EV's chassis and battery could be combined into one ultra-light, super-strong structure, would you feel more confident about driving it, or more nervous knowing the entire car is the battery? Why? Please share your opinion in the comments section below this video. Thanks for watching our video. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to subscribe to Tesla Car World and turn on notifications so you never miss our latest videos. We appreciate your support and look forward to seeing you in the next video. Goodbye.